Okay, so today we will talk about nuclear fusion, or basically thermonuclear fusion in stars, basic physics behind it. Now, in our previous class, we have a lot of discussion on the basics. You must remember, right? We talked about the three sources of energy generation possibilities, right? Gravitational, then chemical, then it was found that these two are not the source. They could not account for the age of the sun. And then we discussed about the fusion, and there we talked about this example, hydrogen to helium, and it was found that indeed through this it is possible to explain the age of the sun and the solar system. And not only that, there are other features as well which can be explained, but we will talk about it eventually. Then afterwards we talked about the various types of nucleosynthesis. Oh yes, before talking about nucleosynthesis, we talked about in this fusion, remember we talked about the binding energy per nucleon chart as well, and then we discussed about how you can explain using fusion the energy released when two nuclei fuse to form a heavier nuclei up to iron. And after that we have to use different mechanisms. Basically we have to use neutron capture mechanisms which don't involve charged particles. Because why? Because heavier nuclei, come on, think about the Coulomb reaction, Coulomb barrier. Okay, it will be huge, immense. So we have to talk about in terms of uncharged particles, and neutron is the one which plays the key role here. Okay, and so after this we talked about the various types of nucleosynthesis, right? So we talked about basic ideas about Big Bang nucleosynthesis, then stellar nucleosynthesis, then explosive nucleosynthesis, followed by cosmic ray spallation. Small discussion about it. Okay, so these are the topics that we have discussed. Yes, and after this we talked about the very important topic of abundance. So basically, why is gold costly, right? And there also the abundance plot, it was logarithmic, and basically the nature is something like this. And now we are set on a, so it was something like this, and now we are set on a path to explain the abundance of the elements, and we will be using our ideas of nuclear physics and fusions, and then we will apply it in stars, and thereafter we will try to explain the abundance of the various elements. And finally we talked about three important factors which play the most crucial role in stellar nucleosynthesis. Remember, we talked about the long exponential tail of Maxwell Boltzmann distribution, and then how quantum mechanical tunneling plays a role, and finally the anisotropy of matter, which is a less discussed topic most of the time. Now what I am going to do is I am going to start off from one of these factors and then slowly proceed. So let me first start with the discussion regarding Coulomb interaction between two nuclei in stars. So okay, so first thing is, let's see if the conditions in our sun are suitable for the nuclear reactions which we have discussed to actually take place. Okay, now let us consider two nuclei with atomic numbers, say Za and Zb. Now, the strong interaction produces a short-range attractive force between the nuclei. And what is the scale? And the strong interaction is present, and the scale is of the order of, say, 1.4 into 10 to the power minus 15 meter. Okay, now you see this strong interaction goes to zero at large distances, and the Coulomb repulsion between the nuclei takes place. So, since we are talking about Coulomb repulsion, then what's the Coulomb energy barrier? Coulomb energy barrier. Well, we know this, and this is equal to Za Zb E square by R, roughly. Okay, I am forgetting the 1 by 4 pi epsilon 0 factor here. Now you see this factor at R is equal to 0. So this Coulomb barrier at R is equal to 0. I am fixing the distance. So this is approximately proportional to Za into Zb. Now let me show you these things dramatically. Diagrammatically. So let's see the diagram. Okay. So basically what I am going to do is do a plot of nuclear separation here, say, and here we have the energy. Okay, now let's see, this is the 0 axis, this is say 1 keV axis. Now why 1 keV? I'll just come to this point in a second. Let me first draw. So I'm drawing a very basic version, right? Okay, so now it is like this. Fine. Okay, now so this potential, this is the potential here, it is proportional to 1 by R, and here let me show you. Let me first draw this. So we are talking about the particle. This is the example that I am going to soon talk about. So before that I am making my graph or so, and again this is not a linear scale, this is a logarithmic scale. This is around minus 2.2 MeV. Now you must be wondering about these numbers. I'll just explain in a bit. And this is say 0.001 R1, and this is R1. So what I am doing here right now, this plot, basically I am showing you the potential energy VR between two nuclei as a function of the separation R, nuclear separation. Okay, now I have considered two protons here, and as you can see, you can calculate for yourself. You will see that for these two protons, the Coulomb barrier, it reaches maximum. Okay, at what? It reaches maximum at around 1 MeV when R is equal to R0, and this is the maximum around this value. Okay, and you see, so at this point the short range nuclear force sets in and binds the nucleus here, and so we have a negative potential energy. Now you see two nuclei with relative kinetic energy of 1 keV, which means typically for temperatures in stellar interiors, they can classically approach each other only to within a separation of R1. Now, what is R1? It is 1000 times greater than R0. Now this dashed rectangle here is basically a rectangular barrier of height. And what is the height? The height is approximately 3e by 2, which we have used to approximate the Coulomb barrier in our calculation of the probability for quantum tunneling. I'll come to this point soon. Okay, so you see we have talked about the Coulomb barrier, right? Now, as I was telling, you see, in the reference frame of one of the nuclei, the other nuclei with kinetic energy E can classically approach only up to a distance, this one. You see, this is the distance. And what is the distance? Just a second. This diagram, basically, it should be this. The particle should be here. Here. This is the point. This is the particle. This is the classical turning point. So, okay, let me write it down. You see, as I was saying, now in the reference frame of one of the particles, the other particle with kinetic energy E, okay, it can classically approach only to a distance, and you know this distance. This is the R1 that I have talked about. So ZA ZB E square by E, right? Now what will happen at this point? At this point it will be repelled away. Okay, now at a typical internal stellar temperature of, say, so typical stellar temperature, say 10 to the power 7 Kelvin, what is the kinetic energy of the nucleus? Kinetic energy of a nucleus is 1.5 kBt, right? 3 by 2 kBt, and this, if you can calculate, basically this is of the order of 1 kV, and you see this is the reason that we have used this particle over here having energy 1 kV. Now the characteristic kinetic energy is thus of order 10 to the power minus 3, right, of the energy required to overcome the Coulomb barrier. Remember, I just mentioned that the Coulomb barrier is of the order of 1 MeV, and what is the kinetic energy is of the order of 1 kV, so 10 to the power minus 3 times, or 1000 times lower. Now typical nuclei will approach each other to a separation of the order of, you see, this R1, which is of the order of 10 to the power minus 12 meter. Now again, this is 1000 times larger than the distance at which the strong interaction force operates. Now perhaps those nuclei that are in high energy tail of the Maxwell Boltzmann distribution can overcome the barrier, right? Let's see. Well, what's the fraction? So let us consider the Maxwell Boltzmann distribution now. So fraction of nuclei with such energies. What is it? Well, the fraction is of the order of minus E by kBt. Okay, so this is of the order of minus 1 MeV by 1 keV. So what is this? This is of the order of e to the power minus 1000. And so, what's this? Come on, students. Calculation time. Well, you will be amazed to know about this number. Look at this power. 10 to the power minus 434. So, do you expect such fraction of nuclei? No, you can't expect that, right? Now, before you can say something, it is important to also know what is the number of protons in the sun, right? So let's do that as well. Now, number of protons in sun, what is it? Let's see. So number of protons is mass of the sun by mass of hydrogen, and this you will see comes out to be 10 to the power 33 gram divided by 1.7 into 10 to the power minus 24 gram. Again, this is of the order of how much? 10 to the power 57. Now look, so we just talked about 10 to the power minus 434, and now compare this with 10 to the power 57 number. So what does this mean? Which one dominates? This one dominates. And so this means that there is not a single nucleus in the sun, right? The kinetic energy required classically to overcome the Coulomb barrier, right? So this means that we infer that there is not a single nucleus in sun with kinetic energy required classically to overcome the Coulomb barrier and undergo nuclear fusion reaction with other nucleus, right? So how do we exist? How are we doing our class, right? How can you see these things? Because what we are, what you are seeing, this tablet, everything, they are made up of elements, right? And they are not just hydrogen, other elements. And where do these other elements come from? Of course, they come from the fusion reaction. But how is this fusion reaction happening in the star? Well, you do know the answer. The answer is quantum mechanical tunneling. And we are really fortunate to have it with us. Okay, so now let's talk about quantum tunneling. Okay, now you see this quantum tunneling through a barrier, it will allow the nuclear reactions to take place. We will see. So let's start with the description of two-body problem. Two-body problem by means of time-independent Schrodinger equation for a wave function in a spherical, for wave function psi in spherically symmetric potential VR. Let's do that. So let us write Now, what is this? Of course, this is the reduced mass mu. So given by Ma Mb by Ma plus Mb, and these are the two nuclei A and B, and they are the masses, right? And we have the potential Vr equal to Za Zb E square by R. Okay, and this is the kinetic energy. Okay, now let us obtain an order of magnitude solution to this Schrodinger equation. Now you see, by our definition, of R1, which is basically the radius of the closest classical approach, we have V of R1 is equal to E, right? Look at here. So these two are equal. V at R1 is equal to E, right? Okay, now so let us write, so we can write V at R is equal to E R1 divided by R. Okay, so I am just using this fact. Okay, and then the mean volume averaged height of the potential between R1 and R0. So mean volume averaged height of potential between R1 and R0. And what is the value of R0? Again, refer to this picture. Here I am talking about the lower values. So the value of R0 is much lower than R1, and this value is, you will see, let us do this. So basically integration 0 to R1 4 pi R square Vr dr divided by, again 0 to R1 4 pi R square dr, and if you do this integration, you will see that it comes out to be this value, 3 by 2e. Now next, let us approximate Vr with a constant function of height, a rectangular barrier that we have used. So this is what we are going to do. We are approximating Vr with a rectangular barrier. Okay. Approximating Vr with a constant barrier, rectangular barrier. Okay, of this height, 3 by 2e. So this is the rectangular barrier height. Then the radial component of Schrodinger equation, it will become h cross square by twice mu 1 by r d2 r psi divided by dr square is of the order of, you see, e by 2 psi. Now this, it has a solution. Psi is equal to e to the power beta r by r, and where beta is equal to root over mu e divided by h cross. Okay. Now the second independent solution of the equation with an amplitude that rises with decreasing radius is unphysical, and we are not talking about it. Okay, now you see the wave function amplitude squared and proportional, what is it? Now if we have this wave function, and if we square it, then that is basically proportional to the probability density for a particle to be found in a given location, right? So we want to do that. So let us multiply the ratio. So let us multiply the ratio of probability densities by ratio of volume elements, right? And this will give us, you will see, the probability that a nucleus will tunnel from R1 to within R0, which is again much less than R1 of other nucleus. Let me show you. So I am talking about the ratio of the probabilities. So basically what I am talking about is this, psi of R0 whole square divided by psi of R1 whole square multiplied by, you see, the ratio of the volume elements. And what is the volume element? So into 4 pi R0 square, right? Here also dr 4 pi R1 square dr. Okay, now this is basically equal to e to the power twice beta R0 e to the power twice beta R1, and this is of the order of, since R0 is much less than R1, so this is of the order of minus 2 beta R1. Now let us write this better way. Okay, so this term e to the power minus twice beta R1, this is basically, you see, exponential minus 2 mu e, okay, divided by h cross, and here ZA ZB e square by e. Again let me rewrite this. So this is basically minus 2 root over mu divided by h cross ZA ZB e square into 1 by root over e. Okay, now you see, a full solution of the Schrodinger equation gives the same answer but with an additional factor. So full solution gives additional factor of pi by root 2 in exponent term. Now if we recall the definition of fine structure constant, remember, so you remember fine structure constant, it is e square by h cross c having value of approximately, not exact, 1 by 137. And let us also define an energy like Eg is equal to pi alpha ZA ZB whole square twice mu c square. What I am going to do is basically I want to write this expression in a better way, and this is why I am introducing these terms. Then you will see, if I do this, then, and following our prescription of minus 2 beta R1 also from here, so if I consider these 3 points, then you see the probability of penetrating the Coulomb barrier this just becomes simplified and we get the probability, I am writing it as GE, is equal to minus e to the power minus EG by E. So this is the probability, where this EG, it is known as gamma window. Okay, this EG here, sorry, this is energy, so this is basically, it is known as gamma energy. Okay, and this factor here, this EG is basically gamma energy, and this GE is known as your gamma factor. I'll talk more about it in later class. Okay, now for 2 protons, again, what is the value? Let's calculate. So for 2 protons, let's calculate the value of EG. EG, gamma energy, is how much? This is pi by 137 into 1 into 1 proton, Z is equal to 1 into 2 half mp c square, and this comes out to be 500 keV. Okay, I'm putting in the value rest mass of proton to be 0.94 GeV, right? So what does this mean? 500 keV. This means that for typical kinetic energy of particle in sun's core, typical kinetic energy is of the order of, having E of the order of 1 keV, we have GE is of the order of e to the power minus 22, right? If you do this calculation here, then you will find this GE minus 22, putting in the value of EG, that is 500 by this 1, 500 keV by 1 keV. If you put in values, then this comes out to be this order, of course after taking in the root, right? So G is of the order of e to the power minus EG by K by E, right? And so putting in the value 500 and here 1 and doing the fraction, it get e to the power minus 22, and this is how much? It 10 to the power minus 10. Now you see this probability is still very low for a given pair of protons, but it is still larger than the classical probability. Compare this. So what was the classical probability? The classical probability was 10 to the power minus 434, and this is your quantum probability from quantum tunneling, 10 to the power minus 10. And do remember that, let me highlight this. So we are talking about this 10 to the power minus 10 and comparing with the classical value. And what about the number of protons in the sun? So we have to compare this with the number of protons, which is 10 to the power, how much? 57. Remember. So what we are going to do now is let us compare these 3 terms. So let us compare this and then compare this with this. So if you consider these 2 factors, 10 to the power minus 57 and minus 434, you will see that fusion cannot happen. But what about this? If we consider 10 to the power minus 10 and 10 to the power 57, you see there is still, this is much larger. So With this, we can explain the fusion using the quantum mechanical tunneling procedure. Okay, so that's it for this class.